Hello everybody, this is Dr. Ali Muqaibel, and now we covered path loss, shadowing, and multipath. Let me start with a quick outline of what we have done and where we're heading. So if you look at the major outlines, we have looked at the objectives for modeling wireless channels. We included link budget analysis in a previous section, and then we went into some physics behind path loss, shadowing, multipath, and Doppler effect. Free space. Now, in this session, we focus on the following: the path loss exponent models. So we have number one, free space path loss model; number two, two-array path multipath model; and then path loss exponent. It does not have to be free space. We have 3.1 and 3.2, single slope, multi-slope. So in this lecture, we are focusing here. In coming lecture, we'll continue with shadowing and then combined shadowing with multipath. Let's just focus on multipath models. This is what we'll do for this lecture. To come up with the path loss propagation models, let's recall the free space path loss, and we'll use it as a first model. Let's say that the signal we would like to transmit is u of t, and now the received signal is r of t. The distance between the transmitter and receiver is d, and hence the time it takes to travel is d over c. The distance divided by the speed of light give you the time. So if we have u of t at the transmitter, what we received is a delayed version, and this amount of delay is equivalent, is function of the distance and speed, of course. So we understand why at the receiver side we have u of t minus tau l, the delay of the path. So the received signal on the other side would be similar to the transmitted signal but delayed version, and of course there will be a phase shift, and this amount of phase of course is function of d. So we have e to the minus j2 by d over lambda. So the distance here controls how much is the phase shift. The received signal based on the free space path loss model will be scaled by the gain of the two antennas and divide by the loss. Now why do we have square root here, and why we have where are the squares for the path loss model? Here we're dealing with the received signal, not the received power. Remember that the power will be proportional to the square of the received voltage. So now we understand almost all the terminologies here inside the bracket. Since this is not transmitted in baseband, it's going to be modulated multiplied by cosine. So instead of saying u of t multiplied by cosine, we multiply by exponential, e to j2 by fc, where fc is the carrier frequency. Now remember that exponential is cosine plus j sine. So we can take the real part. So this term here at the outside is nothing but multiplying by cosine. Taking the real part after multiplying by exponential is equivalent to a cosine, multiplying by cosine. So this equation gives you the received signal as function of the input signal at the transmitter side. Now there are different components here that we need to understand. The distance, there is a distance dependent rotation or phase. I'm matching the colors here, by the way, so that it makes your life easy. So this phase is dependent on the distance. Physically make a lot of sense. We also have a distance dependent power decay, because the amplitude would be decayed with distance. And also we have gain of the transmitter received, of course, is as we said, wavelength plays a role, as does the gain of the transmitter receive antennas. Of course, the gain is measured relative to the isotropic antenna or isotropic radiator. These are the main components: green, red, and purple, or that shows you the main components in the received signal. Out of this path loss, we can come up with a Ferris law. Okay, so this is showing the signal itself, while this shows the power, almost the same. Now, this component, as we mentioned before, is the free space path loss, assuming that we are in free space. So this exponent is always going to be 2 because it comes from the sphere. We have mentioned this before. So now we can say that the received power is the transmitted power plus the gain, and then this is just the dB version of this equation. We have used this before for the link budget equations, where we express the received signal or the received power of the signal through the channel, and we call this the link budget analysis or link budget equation. We can use this and we assume free space and we come up with our first model. So number one, free space path loss model. It's based on first equation. It says that the received power is function of the transmitted power and the gains and the free space. So I can say that the free space path loss, the path loss itself will be a negative sign because we are speaking of loss. And then of course if you want the gain, you take the positive side. Loss and gain are kind of opposite. Path loss of the uncorrelated or unobstructed line of sight. If you have a case like between two airplanes, two satellites where there's no obstruction, nothing, free space, then you might be using this equation and you assume that assuming that you have an isotropic radiator. We have seen that the power decays as a function of d square and it's proportional to the wavelength squared. Of course, once it's proportional to the wavelength, it's inversely proportional to the frequency. This comes from the equation of the antenna, although you don't see it clear here, but because of the antenna fact. Now we go from the first model, which is free space, to the two-ray path loss model. In the beginning, we assume that there is no obstruction, nothing. So we take it one step further, and we see that we have a transmitter here and we have a receiver here. The first line of sight, and then there is a reflection, and hence the name two-ray multipath model. Now the received signal will be very similar to the previous case, but you can see here that I'm modeling the show here. We have one phone here, another phone here, and then there is one line of sight, and then there is one reflection. Let's call this D0, and let's call this D1. And we can divide D1 into D11 and D12 because there are two reflections. You can see that there is direct relation between the heights of the antennas, the geometry, the distances, and so on. So we can find, if this is a distance, we can find the path length by doing some geometry with the angles and so on. So if you want to express this first part is similar to the equation we had in the previous slide, but then we add another one, okay, which is given here. Okay, this equation is for the second path. We can do a little of geometry and show that the two paths could add up constructively or destructively. So the two-ray model is used when a single ground or other reflections dominate the multipath. So in physics, it doesn't have to be just one, but the dominant is one. For example, between two ships and the sea, there is usually a line of sight and a reflection from the seabed or the water surface. Although there could be other reflections, but these are the dominant ones. So don't confuse that. We're just speaking of the dominant reflection, so it doesn't have to be exact. The two-ray model is used when a single ground or other reflections dominates the multipath effect. Okay, like one line of sight and one reflection from, or one bounce or reflection from the ground. All right, so the path phase rotation here, the path phase, the rotation, will depend, of course, on the bandwidth, just like we had before. And the path gain also depends on the distance, antenna pattern, whether we are line of sight, line of sight, and the reflection. So we're just kind of taking one step further. The ground bounce approximately cancels line of sight at some critical distances. If you see the diagram here, what we have in the x-axis is the received, in the y-axis is the received power. Okay, and then we have here the logarithmic scale of distance. You can think of this distance log d to base 10. So you can see that the power in the beginning is the normalized power, we have 0. As we move around, there will be some constructive interference between the two, so the power improves. And then at these nulls, what are these points? What are these nulls? These are the points where we get nothing, where the two paths cancel, or we get very little signal, where the two paths are exactly opposite to each other, constructive, destructive. So you can guess what the wavelength relative to the distance here. Okay, remember this is the log scale. So from these peaks, you can get a hint about what the wavelength is. What we notice here that let's say that we are here and then we are start to move away. This is D. As you move away from the source, you'll find that the power could increase in the beginning and then it goes up, down in a semi-periodic fashion. And the average decay slope is d squared. It's proportional to d squared. This is like free space. Free space was just a slope going down. But now we can see that we have more details. After a critical distance, after distance DC, which we call it the critical distance, what happens is that the slope become, or the decay become proportional to d raised to power 4. So this is the critical distance. We have piecewise linear approximation shown here, and we have a slope of d squared, and then after a critical distance the decay become much faster. In the few coming slides you will see how this happened. If you want more details, the details about geometry, you can find it in Andre Goldsmith section 2.4 of the draft 2020 book. Now if you look at this equation, you'll find that the power fold is independent of lambda, if you assume that lambda is also, although lambda is shown here explicit, but if you consider lambda inside these two expressions, you'll find that the two path cancellation equivalent to two elements array, as if you are receiving two paths or you are receiving by two antennas. It's one way of thinking or another. So the two path cancellation equivalent to two antenna element array, the effect of the aperture of the received antenna is changed. So as you have two antennas or you have two paths, you can equate the two. Okay, so to understand this more, as I said, we will give you a computer assignment, and I think it's fun to experiment with. So work in groups of 3. The assignment will be officially posted. So read the two-ray model, section 2.4, as I just mentioned, and Andre Goldsmith 2020 draft. Produce the figure shown. So your job, of course, is to make some assumptions regarding the height, regarding the distance, and so on. And then I'd like you just specifically just to have differences between you. Let's say that the height of the transmitter is the serial number of the first student, height of the receiver is the serial number of the second student, and then the frequency is the serial number of the third student multiplied by 100 megahertz. I would like you to see the impact of frequency, so you might play with the frequency and compare figures. It's an open-ended problem, so please try to play with things and show me that you understand what's going on. Submit the assignment, including the code, no more than 3 pages, change variables and demonstrate concepts. And just for you to plan, I will estimate at least 3 hours of continuous work to be able to produce the same curve, given that you are doing it for the first time. Of course, if you are fluent in Matlab, you could do this in a much faster time. Okay, so this will make sure you understand the two-ray model. The third model, remember we had the free space Pathloss model, and then we have the two-ray model, and now we take it further by looking at the Pathloss exponent model. So we're not saying free space Pathloss, but we are determining the exponent. So remember that this grayed out equation, we're going now to change this equation. This we have covered before, the free space Pathloss model. In the single slope model, we'll start with the single slope model. We use it when path loss is dominated by reflections, so it's not just free space. We're going to use it for general trade-off analysis of various systems, simple model that captures the essence of the signal propagation without complication. Single slope is very simple. So most important parameter in this model is the loss exponent. We're not going to say this is 2, we're going to make it gamma. And then we're going to look, they're very comparable, but we're going to call the exponent now gamma. Usually it's between 2 and 8, but it could be less than 2. If you are in a corridor, like if you're in a corridor, and then the wave will be reflection, and it will be much better than if your receiver is here, then we get much better signal than free space. So it could be even less than 2 if we have waveguide effect. If we have waveguide effect like in corridors, and then it could be as bad as 8 because of obstructions and so on. So what we are saying here, we have a very similar to path loss, but the decay is not 2, it's more than 2. What causes this is the reflection and path loss that's dominating, because we don't have free space. How do we measure this? We can do it through experiments, like we take a transmitter at one position, and then in the building we start moving and measuring the received power, and we see how much is the decay, and start making some repeated measurements, and then we fit a curve. So for example, it was calculated in in the literature that urban microcells has 3.7 to 6.5. Urban macrocells, big cells, and in urban microcells, smaller cells, 2.7 to 3.5. As it becomes bigger, then we have maybe buildings or so. Office buildings, between offices and buildings, it's about 1.6. As I mentioned here, it could be less than 2, so I'm going to change this. So 3.5. Office buildings, multiple floors, between multiple floors, the transmitter in a floor and the receiver is a different floor is 2.6, 2 to 6. Stores, 1.8 to 2.2. Factory, 1.5 to 3.3. And in home buildings, it's 3. Of course, it makes a difference whether it's a concrete building or wooden building or so. But this is just to give you a rough idea. Now, we're going to use K here. Okay, remember that we have this equation. It's exactly the same equation, but we are rewriting things. So dr is a reference distance where we measure the power there, and let's say 1 meter, 2 meters. dr is we have distance and reference distance. K is going to be 20 log base 10 of lambda over 4 by dr. It comes from the same equation here. So free space path gain at distance dr. K is the distance is the received gain or the received free space path loss at distance dr, at the reference distance. This is why in the substitution here we substitute dr. So K and dr are related, and usually dr is taken to be 1 meters for small size measurements, and it's taken as 1 kilometer for long distance communication. So once again, K is less than 1. Free space path loss gain at distance dr, and it's assumed to be assuming isotropic antenna K would be given by the following equation. So it makes K is less than 1 if we have isotropic, if we have isotropic radiator. Now we have 3.1, which is single slope. Under the same path loss exponent model, we'll have 3.2, which is multi-slope. So just bear with me. So this is just to extend that the received power will be PT plus K times the difference, just converting this into dB scale. Remember that here, if it was path loss, this would be 2. But we have now gamma because the exponent could be different. For the multi-slope, still path loss exponent, but we have multi-slope. So we divide the distance into stages, and because when we took the measurement, we found it's not really linear. So why do we take one exponent? So we have different critical distances or distances. So for the multi-slope path loss, the multi-slope path loss model is given is piecewise linear in dB, and it's generalized version of the single slope model, because if you take it as one segment, it becomes a single slope, and it captures an analytical two-ray propagation model. So the single slope will not fit with the two-ray model. This allows us to capture the two-ray model here, and they also fit well to the empirical measurements. So when we do measurement, we'll find out at shorter distances we have excellent fit to a linear one line, but as we go away, we cannot continue with the same line fit. I cannot just continue with the same line fit, so it's maybe more appropriate to have multi-slope path loss exponent. Okay, this is the case with so we notice that the exponent increases with distance for urban and indoor environments. Usually we have urban and rural environments, and we have indoor and outdoor. A special case, of course, is the dual slope. So dual when you have just 2, multi if we have 2 or more. That's how it looks. We have gamma 1 here, and then we have gamma 1 and gamma 2 for the case of more than. So we have a dr, the reference distance, and then we have the other point which is dBb. In this case we have 2 slopes. Now time for the examples. Okay, so in this example we're saying that path loss exponent model single slope. We're given in this example, given the fact that the received measurement relative to the transmitted measurement is given here, and this is the distance. So what I did in Matlab, I just created a code where I inserted these values, and I can share the code with you in the comment section maybe, and then we just plot these two. So we're taking the relative distance to be 1 meter, and k for this 1 meter, if you substitute 1 here, and for the frequency you can find the wavelength here. Remember that c equal to lambda f. So we can find, by just substitution, I can find the value of k in dB. Remember that here we're using 20. Okay, instead of saying 10 log and then we have square, the 2 would come in the front. So the question is, given this data, can you empirically find what is appropriate path loss exponent for this channel? The one that minimizes the MSE. MSE stands for mean square error. Mean square error between the model and the dB measurement. So we want to draw a line. We want to fit a path loss exponent here. The answer to this question will be 3.71, but we need to see how. And for the second part, find the received power at 150 meter for PT equal to 1 milliwatt. Now remember that 150 is not here, it's something in between. But once we fit the curve, we can use our curve to model. So for that case, it's going to be -112 dBm. It makes sense here because it's in between these two values. If it's outside, then there might be something wrong. So let's see how we got this 3.71 and -112 dBm. That's the best line that fits the curve. So if you draw here a line at 150, remember this is a log scale, so this is 2, 3, 4, 5, 1, 2, 3, so 2, 3, that's 10, 11, okay, this is 20, 30, 110, this is 100, and then 100, and this is 200, so it's something here. Of course, it's not near, so just tell you it's -110. So let's see how we got this number in the following slide. Solution. We want to minimize the following function with respect to gamma. What's the function that we want to minimize? We want to minimize the mean square error. So what's the error? The error is the difference. And we are minimizing the mean squared error. So this is why we have square here. And we're taking the mean by considering all possibilities. Because once you square all of them and add, then we're going to minimize. Whether you divide by 5 or not, we just need to minimize this. Why do we have 5 here? Because we had 5 measurements. So we considered all of them. So the received signal using the model is k plus k minus gamma 10 log. This is coming from the path loss exponent model. And because of the minus sign, now we got the following expression. So what we were going to do is we're going to substitute all possible values, the measured from the table, and we have k known, and the only unknown is gamma here. So k is given, as we mentioned before, and just by direct substitution, I got -31.53 dB. So if we substitute all and then summarize, I'll just show you the expression here in a second. Okay. So this is -70, -75. These are the measurements from the table. And then this is the value of k, as you can see. This is k, so it's repeated. What changes here is, okay, we're trying to, for different distances, we are calculating for different distances, so we got these expressions. Opening the square bracket and then collecting the terms, we got the following expression, approximately. So there might be small variations here. This is just using Matlab, so might be some little differences if you want to be more exact. So how do we minimize this? By taking the derivative and equating this to 0. And for that, you will get the root for this equation to be equal to 3.71. So the received power at 50, once we model, we can now use our model to to calculate the receipt power at 150 meter. So I'm just substituting 150. This is the value that you find for gamma, and we got minus 112.27 dBm. Okay, so as we said, that the measurement deviates from the single slope model, and this could be attributed to shadowing, because so far our three models, whether free space Pathloss model or two-ray model or Pathloss exponent model with two variations, which is single slope, multi-slope, all of them we did not consider shadowing per se. We did not have a random model for the shadowing. So this motivates us for the next topic, which is shadowing. You can play with this example, you can change the numbers and see what you get. Here is the differentiation and the answer to 3.71. Alright, let's test our understanding with the following exercise. Please take it seriously, and if you do it right with numbers, then you can claim the understanding. Estimating path loss parameters. The table shown here lists a set of empirical path loss measurements, so PR over PT in dB, for different distances. So this is distance in meters. Assume a carrier frequency of 2 GHz. Now what you have to do is first find the parameters of a single slope path loss model. It's a line, so you need to define two things, K and gamma, that best fit this data, assuming K is calculated from free space path loss at a reference distance of 1 meter. So you can get back to your equations. We need to fit a line to this. You can assume mean square error, minimum mean square error. And then of course the second part, once you find the fit, once you find the model, we will find the path loss at 2K, which is not here. So we'll extend this to 2K. Find the path loss at 2K kilometers based on this model. Write your two answers in the comment section. We'll challenge you here if you can get the correct answer, and if we can get the same answer for different audiences. Thank you. We'll see you in coming video. Watch for shadowing.